Hello to all chemists. Today we're doing some heavy-duty chemistry. We'll be synthesizing sodium cyanide. I need it for my scientific research, and obviously you can't just buy it off the shelf. So we'll make it ourselves. We'll also analyze its purity, because while this particular synthesis method has been shown on YouTube before, nobody has actually analyzed the purity of the final product. We're going to fix that. Spoilers ahead, I managed to get a sodium cyanide sample with 95% purity, which is perfectly fine for my goals. First, a quick disclaimer so YouTube doesn't ban me. This process was conducted in a professional laboratory with all necessary safety gear and precautions. I strongly advise against repeating this. To keep you from trying it, I am intentionally omitting key details like precise proportions and exact reaction conditions. This is just a high-level overview of how I did it. Now, on to the chemistry. The process I'll be using has been known since the 19th century and is well documented in scientific literature. We'll run the synthesis in 2 steps. First, we fuse sodium carbonate with urea to get sodium cyanate. Then, we fuse the sodium cyanate with charcoal at 800 to 850 degrees Celsius to yield sodium cyanide. There's a small issue with commercially available soda. It isn't pure sodium carbonate, but rather a crystalline hydrate containing water. Water interferes with our reaction, so first we bake the soda in an oven to dehydrate it completely. Next, we melt the soda with urea. This process is similar to how I made calcium cyanate in my video 2 episodes ago. The urea needs to melt and then the mixture hardens. The reaction proceeds the same way, except this mixture hardly foams at all. Once we've prepared the sodium cyanate, we mix it with an excess of charcoal. It's better to use granular charcoal rather than powder. We load everything into a stainless steel crucible with a lid and place it in a muffled furnace at 800 to 850 degrees Celsius for a couple of hours. Once gas evolution stops, we pull the crucible out. You have to be extremely careful here. Cyanide can vaporize at these temperatures, so I wore a gas mask. We pour all the cyanide out onto a metal surface. After it cooled down, I crushed it, first using a mortar and pestle and then in a coffee grinder to get a fine powder. Now let's move on to the analytical part. First, I wanted to determine the concentration of cyanide in the raw melt. I found a great titration method using a nickel salt solution in the presence of dimethylglyoxime. Here's how it works. We drop a nickel salt solution into the cyanide solution, adding a small amount of the indicator, dimethylglyoxime. As we drop the nickel solution in, it reacts with the cyanide according to this chemical equation. As long as there is cyanide in the solution, the nickel will react with it. But as soon as the free cyanide is completely used up, the very next drop of nickel solution instantly reacts with the dimethylglyoxime, forming a red precipitate. That signals the end of the titration. By measuring the volume of the nickel solution consumed, we can calculate the exact amount of cyanide in our solution. For this analysis, I had to buy a bit of extra lab equipment. Here I've already prepared the nickel salt solution. Now let's prepare the cyanide solution. I took exactly 1 gram of my crude melt powder and dissolved it in a small amount of water. I also added some ammonia to the mixture. I filtered the solution to remove the charcoal residue and washed it a few times with water. Then I transferred the solution into a volumetric flask and brought the volume up to 100 milliliters. Here I am filling it up to the mark. Next I took 10 milliliters of this solution and added a couple of drops of dimethylglyoxime indicator. Now we can start the titration. I began dropping in the nickel salt solution. At first nothing happens, but watch what happens near the equivalence point. When a drop hits, the solution temporarily turns dark and then clears back up. This means the titration is almost finished. Shortly after, another drop makes the solution turn dark and stay dark. That's the end point. After a few seconds, the dark solution turns pinkish red, which signals the formation of nickel dimethylglyoximate. The titration is complete. According to my calculations, the cyanide content in the crude sample was around 30%, which was the best result I could get at this stage. To get pure cyanide, we need to extract it from the crude melt. I'm going to use methanol in a Soxhlet extractor. For 100 grams of melt, I used 250 milliliters of methanol and extracted it for 2 days. Here's the result. Inside the extractor, we have a liquid with a precipitate. I filtered out the precipitate and evaporated the methanol. Then I analyzed both the precipitate and the filtrate separately. The cyanide concentration in the precipitate was around 30%. I got 15 grams of it, while in the evaporated solution it was around 90%. I also got 15 grams of this. I wasn't satisfied with this outcome. For my research, I need at least 95% purity. So next I tried drying the methanol over magnesium. Here it is drying. It took me about 5 hours. Then I distilled off virtually anhydrous methanol and used it for extraction, running it the exact same way. Here's what I got: 4 grams of precipitate and 10 grams of powder from the evaporated methanol. There was almost no cyanide left in the precipitate, only about 5%, whereas the sample from the evaporated methanol reached 95% purity, which completely satisfies my requirements. That wraps up my experiments for today. Thank you for watching, and goodbye.